Okay, welcome to this very special edition of Chemistry 111. I'm doing this in lieu of Wednesday class, so we're going to finish chapter 8 and look a little bit at the homework. So let's get right on going. So last class, real quick, we had just previously gone through how to look at oxidation numbers. We briefly went through how to look at oxidation numbers and how to determine oxidation numbers. Well, how is this going to be used? Well, we need to be able to recognize common redox reactions. Those numbers are often difficult to determine, but most of the times recognizing a redox reaction is not nearly as difficult. The most common redox reaction and the easiest to notice is a single displacement metathesis reaction, where one element swaps with a compound to produce a different element, like aluminum plus iron oxide forms iron and aluminum oxide. What makes it so easy to determine this is a redox reaction? Rule 1 on determining oxidation number is all elements are inherently zero. So aluminum has an oxidation state of 0. Iron has an oxidation state of 0. The iron in iron oxide turns out to be 3+. But the fact of the matter is iron in a compound is not 0. So iron must have lost or gained electrons to perform iron solid. Aluminum in aluminum oxide is not 0. So aluminum must have lost electrons in order to become aluminum oxide. Anytime you see a pure element formed or a pure element consumed, these are redox reactions and could be easily observed as such. Many combination and decomposition reactions will also be redox reactions, but that is not always true. So be careful. Also, all combustion reactions are redox by proxy, because anytime you react pure elemental O2 or oxygen, you're going to go from oxidation state of 0 to oxidation state of -2, regardless of what the other charges are. In all redox reactions, we will see an equal number of electrons lost and electrons gained. One atom will undergo a loss of electrons, which is the oxidation, and the other atom will gain the electrons, which is called the reduction. As we see in the reaction there, aluminum plus chlorine forms aluminum chloride, a standard combination reaction. Aluminum is going from 0 to 3+, so it is losing electrons, becoming more positive, and is oxidized. And chlorine is going from 0 to 1-. It is gaining electrons, so it is being reduced. Now, this is where it gets a little tricky, but we call the chlorine as the oxidizing agent because it is used to oxidize the aluminum. Aluminum is thus the reducing agent and will reduce the chlorine. No matter what, though, in a redox reaction, there is both oxidation and reduction. If you can notice one, there is another one there, even if you don't necessarily see it right away. Okay, so here are some simple examples of oxidation reduction reactions. Well, I say simple, but I'm lying. Some of these are simple, some of these are not so simple. 8 protons plus dichromate and iron 2 oxide goes to iron 3 oxide, 2 chromium 3 pluses, and 4 waters. So What would be the easiest way to notice that is oxidation? Dichromate is going to be a pain in the butt to determine the charge. If you do determine the charge, you find chromium to be 6 plus. 6 plus to 3 plus means chromium is being reduced. Iron, this is a little bit easier. Fe2O is so 2 plus, 2 minus. So that is iron 2. That's going to be 3 plus, 2 minus. So seeing how iron changes states pretty obviously right here, we know this must be redox. Carbon monoxide plus oxygen gas to CO2 gas. This is a combination reaction or a combustion reaction, depending on how you want to look at it. Either way, we're using pure elemental oxygen. So it is an oxidation reduction reaction. Hydrogen peroxide decomposes into water and O2. You're forming a pure element from a compound. So this one is clearly a redox reaction. And of course, the thermite reaction, which is often used and abused here. A single displacement. So we can have all manners of reactions going on here. But pure elements, pure element, pure element, those are dead giveaways anytime you can find that. Okay, and lastly, these redox reactions have a certain strength to them. Just like strong acids and strong bases, we have certain possibilities. So that all single displacement reactions are redox. But there's certain reactions that will happen with acids. If I mix calcium with water, it will form calcium hydroxide and hydrogen gas. If I mix cobalt with water, nothing would happen. But when I mix cobalt with hydrochloric acid, it forms cobalt chloride and hydrogen gas. This reaction of metals with an acid is called corrosion. Not all of these reactions will occur. Not all reactivity can be categorized into the following activity series. Not all of the single displacement reactions will occur. So I can't mix I can mix calcium with calcium metal with cobalt chloride and make calcium chloride and cobalt solid. But I can't mix cobalt with calcium chloride and expect an exchange to occur. And this is because any metal higher on the table will always replace a metal lower on the table. It's essentially, there is a steep hill, and the higher up on the table, the steeper the hill, the more likely it's going to roll down. Elements would have to go back up to replace the guys above them, and so it's not going to happen. So hypothetically, iron plus copper oxide goes to iron oxide and copper solid. You see iron's right there, copper's right there. So iron will replace copper. But if I put iron oxide in copper solid, you get no reaction. So it's going to go one way, but not the other. So we could use this activity series to predict whether a redox reaction should occur. So potassium, barium, strontium, calcium, sodium will react violently with cold water to give hydrogen. These guys, magnesium through cadmium, will react with steam. So it needs hot water, boiling hot water to react, but it will react. Cobalt, nickel, tin, and lead will react with acids to produce hydrogen gas. And there's hydrogen right there, the 0 point. And everything below this, so antimony, bismuth, copper, silver, mercury, palladium, platinum, I'm sure gold's down there, will not react to give hydrogen. So acid will not do anything. The higher up the table, the less energy it needs to react. The lower, the less likely it will react at all. Okay, that is all of this chapter. With that in mind, I want to. Oh, come on, Macmillan. I want to look at some of the homework associated with this. There is some stuff due, I think, this week, but it has to do with Chapter 6. The stuff, Chapter 7. The stuff, there's nothing due the following week. However, there is some stuff due. There is some stuff that it happens to be due. Okay. Yeah. In 2 weeks' time when the test is supposed to occur. So the test might actually be before the homework is due. But so be working on this. Be working on it. There's actually 2 parts to Chapter 8. There's an 11 question assignment and a 13-point assignment. This is the second one. So write the balanced molecular equation for the neutralization of HI and barium hydroxide. So hydroiodic acid and barium hydroxide in aqueous solution. So and it says include physical state. So what we're looking here is HI, and we'd put in aqueous plus BaEA OH 2. Shoot. Aqueous. Do the arrow. And then I'd have H2O liquid. This to avoid my hotkeys. O liquid plus EAI aqueous. Now we'd also have to balance things. Since there is 2 I's, there has to be 2 HI's. Let's check answer. Oh, shoot. What did I do? Oh, I know what I didn't do. Try again. I forgot to balance my waters. With that in mind, now try. Yes, so that is just fine. That's an example. So being able to write an equation, predict the answer based on just the starting thing, that this is an acid base. This is an acid base. Acid base forms water as a product. Now, a similar reaction. Write the Net Ionic Equation, including the phases. With this in mind, I would write this as 2H plus, 2Br minus, Ba2 plus, and 2 hydroxide goes to H2O and 2H2O and Ba2 plus and 2Br1 minus. Almost all acid-base ones can be simplified as H plus and OH minus goes to H2O. Yes, it should be 2, 2, and 2, but we can simplify that and divide everything by 2 and get 1, 1, and 1. So I don't need to view the solution. I got it. Now this one is a tricky one. And that's why I gave this one on the problem. This one is start by splitting only the strong electrolytes. And here we have strong acids and strong bases and soluble aqueous salts. So they give you a list of all the strong acids and strong bases. Any non-strong acids would be, by definition, a weak acid. So strong acids is HCl, HBr, HI, H2SO4, HNO3, HClO4, and HClO3. And strong bases are these guys. So with that in mind, that guy is not a strong acid. That guy is a strong base, but that is a weak acid. So when we go to split that, you would have that HCN and OH minus. But it'd still swap over. And so you just can't cancel the CN out because the CN is in a compound on this side and it would be by itself on that side. So identify the oxidation state of barium 2+. Well, it's 2+. The sulfur and sulfate, we did that one. Sulfur and SO2, the zinc and zinc sulfate. So identifying oxidation states are examples of problems. Identify the oxidation states in each element. Remember, oxygen is almost always 2-. You can look up what is the oxidation state of chromate to give you a hint on how to figure out chromium. Once you have chromate and chromium, you can figure out what is manganese. Well, this guy is a little bit harder. Put these guys in order of oxidation agents. But to do that, you can't really do that without either guessing or looking at the activity series. Remember, the guy higher on the table is most reactive, and the guy who's most likely to be oxidized, to lose its electron. An oxidizing agent would be the guy who gets oxidized would be a good reducing agent. The guy who wants to be reduced, which is on the bottom of the table, would be the best oxidizing agent. So you gotta work through that. Write a balanced equation for rusting of iron, which iron reacts with oxygen and form iron oxide. So writing a chemical equation based on that. Balancing the single displacement. So you have to first make the products and then balance it. Silver is +1, it would go to silver solid. Aluminum is solid, it would go to aluminum 3+. So you'd have to mix those together and figure that out. Net ionic, copper nitrate, iron metal. Here's a cool little interactive. There's a cool little interactive where you've seen these react and seen. Write the net ionic equation with iron metal and copper nitrate. Metal and copper nitrate and see what happens. Pair these guys. Pairs will result in a chemical reaction. So once again, we need to go to our activity series. The guy higher up on the table will replace the guy lower on the table. So is lead higher on the table than magnesium? Or is lead lower? That guy, lead, if it's higher, would react. Lead, if it's lower, will not react. Same thing, gold and chromium. You look and see where they're at on the table. And then another activity series problem. So this one is mostly about acid base and oxidation reduction, these 11 problems. Let's look at the other set of assignment. The other set is basic balancing equations and also precipitation reactions. The first one, the first couple problems is balance this equation. So not too bad. We have one of recognizing whether this is a single displacement, double displacement, combination, decomposition. I'll give you two of these. Lead and nickel swap places. That's a double displacement. Lead hydroxide splits into lead oxide and water. That is decomposition. This would not be a reduction or redox reaction because lead is 2 plus, lead is 2 plus. O is 2 minus, O is 2 minus. H is 1 plus, H is 1 plus. PCl3 plus Cl2 goes to PCl5. This is a redox because chlorine is 0 and then chloride in both these cases is 1 minus. So there is a reduction there. So more classification, you could label these as acid, base, precipitation, redox, or none. So acid base, you're looking at water formation, proton and hydroxide neutralizing. If it's not doing that, it's not acid base. Precipitation is solid formation out of two solutions. If there's no solid forming out of a solution, it is not precipitation. If there's already isn't, it's probably not a precipitation. And finally, redox. Is there a change in oxidation number on any element? If there is a change, look for and identify the second element, and then it's a redox. If you cannot find the second element, you may be mistaken. And if it's neither of those, then it might be just none of the above. It might still be a combination or decomposition or something like that, or double displacement. It'd still be a no reaction. Still be none of those three types. Conductivity, there's a neat little conductivity interactive that I'll try to show you in person. But click on that and I'll pull that up and I'll show you which one of these guys are strong electrolytes, which are weak, which are non-electrolytes. Classifies strong acid, strong base, and salt. And acids have at least one ionizable hydrogen. Bases usually have one or more hydroxide. Salts are ionic compounds that have neither. So NH4 is a weird example, but so calcium hydroxide would be a base. Lithium chloride would be a salt. This guy is oxalic acid, has some hydrogens it can lose. So, strong electrolyte, you got to look at these guys and maybe look at the hint, maybe go back to, you got to think about what these are made of. May go back to that interactive. We have here, complete the equation for the dissociation of cadmium into, essentially you're splitting the molecule into its ions. That's all they ask. Split it into its ions. Then we have select the anions, whether it's soluble or insoluble. There's a video to watch. Oh, for God's sake. There's a video to watch. I will show you the table later. Whether soluble or insoluble, I think they'll have table solubility. Yeah, here's a table. This is a table like I will provide for you. If I don't already have it in the classroom notes, I will provide this for you shortly. So right here, cross-listing is solubilities of common salts. Everywhere there is a blank or white space, these are soluble salts. So sodium, potassium, these are soluble. Magnesium, soluble, 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 insoluble with hydroxide. Soluble, 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 insoluble with sulfite, phosphate, carbonate. And so you can cross-list here to see whether these would be soluble or insoluble. And there's the rules below there. And there's a couple things like, oh, slightly soluble, blah, blah, blah. Magnesium sulfide decomposes. Most oxides react with water to form hydroxides, so they won't hang around. So that chart will be given to you. It's better that you learn how to use it than you memorize the rules. But if you know Rule 1 and Rule 2, that gives you a big hint. Looking at this, solubility rules, complete and balanced defined reaction. So you need to double displace these guys and then determine, is a solid going to form? If a solid forms, make sure you put in your states of matter. That's why you have to include your physical states. So this one is just write the full reaction. 11 is predicting whether a precipitate would form. And you have to do this interactive. You have to do this interactive to see what this is, because you're looking at what anion do you have. It's a neat little interactive where you mix lead, nitrate, and barium with various things, and you'll see which one precipitates and which one doesn't. From that hint, you can figure out what is the mystery solution. Finally, the last two, so you do a molecular equation and a net ionic equation for that, and another net ionic equation. So this is what the homework for these two chapters looks like. With that in mind, I know this has been short. Be working on your homework. I will be available. You can contact me if you have any questions, but be working on your homework so that when we come back from break, you'll be ready to do some review and knock the test out. I don't want it to be too hard, but I do gotta see that you know what you're doing. So thank you for stopping in, watching this. See you later.